Hey guys, welcome back to quantum mechanics. This is Friday the 4th. Yes, it'll be Friday the 4th when you watch these videos. Last time we started our discussion about scattering theory, and so I reviewed kind of the basic idea of one-dimensional scattering, which you should know or you should know from your undergrad days, but make sure you know it if you haven't taken a qualifier yet, because there's a chance that one-dimensional scattering problems can show up, especially like scattering off of delta function potentials and things like that. Um, but what we do in graduate uh, level quantum mechanics is study three-dimensional scattering. So we're working in the real world. And so what I did last time was kind of started with an overview of scattering in three dimensions. And the first kind of complication that you run into is that you're not dealing with a point particle anymore. That typically in these types of experiments, you have a beam of incident particles, and these particles are kind of formed into bunches, and they have some finite spread in the transverse direction. So if this beam of particles is moving from left to right, there'll be some kind of spread in the particles. And this spread is not evenly distributed, so it's kind of uniform in the middle, but then that uniformity kind of dies off as you go out away from the axis. And this direction we typically call rho, and so rho will have some maximum value that we call the impact parameter. But in most cases, you don't really have to worry about the full spread of the beam, because the scatterer, the potential is typically a lot smaller. The range of the scatter is typically a lot smaller than the spread of the beam, and that's what this picture is trying to denote, is that this is the kind of the general setup that we're looking at. So we have some beam of particles, and we're shooting it off, or scattering it off of some potential, whether it be a Coulomb potential or some kind of screened potential like a Yukawa potential or something like that. But anyway, so the setup's like this. So we have particles coming in this way. We typically define this to be the z direction, and we align our wave vector in that direction. This thing will assume that it has some spherical symmetry, so it's not going to look like this kind of like whatever this odd shape is. But for whatever reason, I drew it like that. So what we're trying to compute is basically the probability that this beam comes in, scatters off of this potential, and then we detect it at some angle, theta and phi, which is not shown here, but in some detector at some particular angle away from the axis. And that quantity is what we call the differential cross section. So it's basically the number of particles scattered into this detector per second, divided by the number of incident particles per second per area in this rho plane. Okay, so it's basically number of particles that go into this detector divided by the number of particles that scatter off of this, or that are incident on this potential. Okay, and typically what we do is we start by writing down the complete wave function for this situation. So the complete wave function, much like in the case of one-dimensional scattering, is that you have some incoming wave, right, or incoming particles, and those you represent by a wave, and typically it's represented by a plane wave, right? And then the scattered wave is some type of spherical wave. So think of like in a lake or a pond, when you drop a rock in there, and the waves kind of go away from it. You can think of that picture when you think of the scattered wave, right? So the beam of particles comes in, hits this thing, and then emanating away from this potential, you have kind of spherical waves. Okay, and so that's how we typically write the wave function in two pieces. So the incident wave, which I said is going to be a plane wave, and the scattered wave, which is going to be a spherical wave. And let me not go through these things again because they were super confusing. Okay, so let's see how this works in a little more detail. Okay, so again, we're choosing the z-axis to be parallel with our plane wave. Okay, so or the wave vector of our plane wave. So our complete wave is going to look like this. So it's going to have this e to the ikz. So this is our plane wave coming in, and then we'll have some scattered wave. And the scattered wave, like we said, is going to be spherically symmetric. So it's going to have some dependence on theta and phi, and also it's going to have some dependence on the radial piece. Right. So even though this thing, the form of this thing is going to depend on the form of the potential, we know that when we get very far away from the scatterer, from the potential, that this scattered wave, which is that's what this subscript here is SC, is this going to look like a plane wave, or sorry, not a plane wave, but a free particle, right? It's not going to have any. It's just going to look like a free particle, right? And so, in other words, very far away, it's going to satisfy the normal wave equation. And just by using our physical intuition, we know it's going to be purely outgoing. Okay, so that means we're dealing with a spherical wave that's purely outgoing. We'll deal with that in a second. But spherical wave, we know from last semester, we can write in this very kind of abstract form, right? Where we have we've broken the wave into spherical and radial pieces. So the spherical piece, we know the solution to this wave equation are the spherical harmonics, right? And we learned last semester that the solution to the radial part of this is some linear combination of spherical Bessel and spherical Neumann functions. Now, last semester when we were dealing with solutions to problems of spherical symmetry, we always had the origin included in our region of interest, and so what we did was we know that the Neumann functions blow up as you take R to infinity. Here we've got the opposite case. So R, the origin in this case is going to correspond to the center of this potential, right? And so since we're considering regions out here, we're going to have to keep the Neumann piece, the Neumann piece of the wave function. Okay, so we don't have the luxury of setting this coefficient to 0, so we're going to have to keep both pieces. However, we can simplify things a little bit because we're dealing with, out at basically R, we're dealing with basically R goes to infinity, right? Because the range of this potential is very, very small, microscopically small, compared to this macroscopic distance of, between where the scattering takes place and the position of our detector. So what we can do is we can actually take those spherical Bessel and Neumann functions and expand them for large R, right? And we saw last semester that these things for large R look like basically sine functions over 1 over R, or cosine functions over 1 over R. All right, so typically what the approach is, and I'm just going to kind of step through it, is that you take the large R limit, you rewrite these guys as exponentials using the normal Euler functions, and then you require. So now we use the constraint that we have a purely outgoing wave, and when you have that, you're able to figure out a relationship between these coefficients. And to have a purely outgoing wave, their ratio has to go like minus I. Okay. So in that case, let me go over here. So let's go over here. So in that case, we can write the scattered wave like this. So here's our radial piece that's coming from expanding the so from expanding the Bessel and Neumann functions, right? Here's our spherical piece, and then here's our coefficients, okay? And typically what's done is that all this stuff, this complicated looking mess, gets lumped into this nice little symbol that we call F, which is, we know, is only depends on theta and phi. So it only depends on the angular pieces, right? All the radial dependence is out in this piece, right? This is a spherically outgoing wave, okay? So that means the scattered part of our wave function just has this nice simple form, okay? And we'll deal with what this thing is much later, okay? But for now, let's just keep it written as this nice little function f of theta and phi, okay? So that means that our total wave function, including the plane wave, just looks like this, okay? And this thing, because it's the amplitude of the scattered wave, has the very inventive name of, or the imaginative name of, the scattering amplitude, okay? And we'll see how that comes into play when we're trying to compute cross sections, and we're going to see that, I don't want to spoil it for you, but we're going to see that this thing is going to be kind of our the main object that we want to focus on. Okay, so I guess we're going to do that now. So let's see how do we want to compute the differential cross section if we know the form of the wave function. Okay, so to compute the differential cross section, there's a few things that we need to know, right? So we need to know the ratio of the probability flowing into our detector, basically, right? And that we're going to call J scattered. So J here meaning the current, the probability current scattered into that detector, and that we're going to divide that by the incident current density. So this J incident, right? So what we can ask ourselves first is, what are these things, right? And if you remember back, I mean, one of the first things you learn in quantum mechanics is about the probability current density. And you know that it has a form, something like this, where you basically take the gradient of the wave function, multiply it by its conjugate, and then subtract the vice versa. And it's got some factor of h bar over m out in front, okay? So what you can see easily is that any current density is going to be quadratic in the wave function, or in our case, the total wave function. But for us, the form of this thing implies, a complication. It implies that the current densities are not only going to be quadratic in the incident and the scatter waves, but there's going to be some cross terms, okay? And that would be a mess to try to deal with, so we can try to simplify things by using our physical intuition. And the first thing that we can do, the first way we can kind of untangle this mess, is to note that as we go back to wherever our particles are being shot out of, and you can think of that as taking r goes to infinity, right? And this should say, this is a little note to myself, but it should say this is where we, I guess, shoot the particles, right? Not detect the particles, but where we shoot the particles from. So we're taking the angle theta. If you go back to this picture, we're taking the angle, so we're going back this direction, right? But we're going back in the, I guess, well, theta equals pi here. So back towards where the particles came from. Where was I? Yeah. So we're going to take this limit as r goes out back to infinity, or however you want to say it. And when that happens, the plane wave piece is going to dominate, right, of the total wave function. And the reason is because as I take r goes back to infinity, this thing's going to die off, right? So as we go back towards the gun, or back towards our accelerator, or whatever they call it, the only piece that's going to contribute, or the only piece that's going to really be there, is going to be our plane wave. And that makes sense, right? Because we're very far away from the scatterer, and we're back in the back towards where the accelerator is. So in that case, our wave function basically just boils down to the plane wave, right? And so I can compute the incident part of the current by just plugging in the plane wave instead of the full wave, right? And if I do that and I take, you take the derivatives and do all the simplifications, I get that the incident current goes something like h bar k over m. Okay, so that's one half. So we've got the incident current, and what we need now is the scattered current. The problem with the scattered current is we can't use the same trick, right? Because there's never a situation where uh, the scattered wave dominates over the plane wave. However, there is another trick that we can use, right? Because we know that our beam, even though we represent it as a plane wave, is not going to be a true plane wave in the sense that it extends in all, it extends over all space in this, I guess, XY plane, right? There's going to be some finite range to this thing, right? So in terms of our impact parameter, we call that rho max. So this thing right here is only going to have a range of 2 times rho max, right? And so the basic idea is that if we look at directions or angles that are far away from the beam, right, the beam of these particles, then the dominant piece of the wave function should be coming from the scattered wave, right? So what I was saying back here about how the scatter wave never dominates is because I'm talking about in the forward or backward directions, right? But in these directions where you're off the beam, right, where there's some finite angle, the scattered wave should be the dominant piece. Where was I? Yeah. Yeah. Okay. All right. So only as we move away from theta equals 0, only the scattered wave piece is going to dominate. Okay. Yeah. Okay. So that means that for theta not equal to 0, our scattered current, we can compute by just plugging in our scattered wave. All right. And we know what the form of the scattered wave is. It's the scattering amplitude, that f function, times e to the ikr over r, right? And we know what the form of the gradient is in spherical coordinates. It has an r piece, r derivative piece, a theta derivative piece, and a phi derivative piece. But the thing to notice about these two guys is that they have 1 over r dependence, right? So if we're taking these derivatives out at r goes to infinity, then these terms are going to be negligible compared to this guy. So we can drop these derivatives and only have to worry about taking the r derivative. All right. So if I plug that wave function in and I take this r derivative, right? So obviously this thing by definition doesn't have any r dependence. So you can pull it out and then take the derivative of this thing, right? The exponential term is going to give you this. And then the derivative of this guy is going to give you a 1 over r squared piece. But the 1 over r squared piece is going to be negligible out at r goes to infinity compared to the 1 over r piece. So this derivative just gives us this, right? And then I can do the same thing for the psi starred piece, right? And when I do that and I put it together, I end up with a scattering current that looks like this. So it goes like f squared, our scattering amplitude squared. There's a factor of h bar k over m. And then there's a 1 over r squared. And this guy is pointing in the radial direction. Okay. All right. So now that we have the scattered current, what we really want to compute is the rate at which these particles are scattered into this solid angle, right? And this is just given by taking this thing, our scattered piece, and dotting it into basically the cross-sectional area of that detector. All right, the cross-sectional area of that detector is given by it's r squared times d omega, and then it's it points, if you will, in the r hat direction, right? So if I plug in for what J scattered is and take the dot product, I end up with this thing, okay, for the rate. Okay, and then if you go back to our definition of this um, of the differential cross section, you'll see that uh, it basically boils down to the ratio of this rate that we just computed divided by the incident current. And when I plug in our expressions, what you see is that everything drops out except our f squared term. Okay, f squared times, and then we have this d omega piece that's coming from the rate calculation. Right, so I can cancel the d omegas on both sides. Right, so here I've multiplied and divided by d omega because I want the differential cross section. Right, and so what I find is that the differential cross section is nothing but the modulus squared of our scattering amplitude. Okay, and I put this in double boxes. It probably should be in a triple or quadruple box. It's that important. Okay, so once we compute the scattering amplitude, if we're after an observable like the differential cross section, all we have to do is take the modulus of that thing squared. Okay, and you'll see this should be etched into your brain because we're going to go back to it time and time again anytime that we need to compute scattering cross section. Right, all the work, this is the easy part, right? All the work's going to go into computing this thing, right? This is where our perturbation theory and stuff is going to come in handy. Okay, and we'll derive a whole kind of recipe or algorithm to computing this guy F. Okay. Before we do that, though, I wanted to touch on something called Fermi's golden rule. Okay, and this is kind of a old piece of physics, but I like it because Fermi was always famous for doing these kind of quick and dirty calculations. They were quick and dirty, but they were usually pretty precise and contained a lot of physics. So I wanted to go through this before we start out on our kind of perturbation theory stuff. So let's consider a system, right? So this is a system that's subject to a periodic perturbation. Okay, so for an example, might be some projectile particle that interacts with the target potential. Okay, and what we can do is we can approximate interactions of these sorts by using a linear combination of sines and cosines. Right. So in other words, I can just write my perturbation or my interaction term as some constant piece that doesn't depend on time times e to the minus I omega t, right? And the reason we do this is because it's a little easier to handle with this exponential, as you'll see. So let's suppose that we have some system and we turn the perturbation on at t equals 0, and we measure the system at some later time t, right? And what we're after is the amplitude for transition from the initial state to some final state. So what's the amplitude, the probability amplitude, we'll find the system in a different state after we've turned this potential on and off. Okay. So the way we do that is to use our time-dependent perturbation theory. Okay. So we would want to compute this coefficient. Which reminds me, I'll put a homework assignment in the Dropbox after I'm done with this. Dealing with this type of stuff. Not Fermi's golden rule, but computing perturbation, time-dependent perturbation theory stuff. Okay, so what we have to do is compute this coefficient, right? And so what I do is I plug it in, right? So this is the piece that's coming from the time dependence of the states, and this omega here is coming from our perturbation. So this omega is different than the omega that we're used to. So this omega is controlling this this kind of sinusoidal potential that we're dealing with. Okay, but the thing is that this guy is the time. It doesn't have any time dependence, right? So we can pull that outside of the integral, And once I do that, then I can do this integration, and it just gives me something that looks like this. Okay. And if I square it to get the probability, I'll get something that looks like this matrix element squared, and then this is the stuff that comes out of the integral, and that's squared. Okay. And if we want to compute the rate, so typically what you're after is not just the probability, but the rate, the transition rate. So how fast do these transitions occur? We would just want to take our probability and divide it by time. Okay. But what Fermi said was, okay, well, what happens if we wait a long time, right? If and an equivalent way of thinking about this is that, what if the interaction happens for a very, very short period? In other words, compared to the time that it takes the particle to get from, the accelerator to the part where it interacts, that time difference is very large, right? So it takes a long time for the particle to get there. It interacts very quickly, and then it takes a long time for the particle to get to our detector, relatively speaking, right? So this is what we're after, right? So we're thinking about this, but we're thinking about it in the sense that the interaction, it only happens for nanoseconds or something like that, um, and so what we want to do is see if we could somehow approximate this thing without having to do the full calculation. Okay, so what we're going to do is we're going to consider the case where the system is exposed to the perturbation, and it's going to be exposed between, so our initial time is minus big T over 2, and our final time is big T over 2, and we're going to let big T go to infinity for convenience, okay? So what I have is basically the same integral that we had before, except now I've replaced the limits on our integration. Instead of 0 and t, we've got minus big T over 2 and plus big T over 2, which are basically just minus and plus infinity. Okay. So again, this guy is independent of time, so I can pull it outside, right? And then when I take this integral with this limit, it's just basically the integral representation of the delta function. Okay. So I've got my coefficient, transition amplitude, just being this thing, right? And if I want to compute the probability, I should take this thing and take modulus squared, right? So that's what I do in the next step. And what you see is you get this thing with the matrix element squared, some constants out in front, but you get this weird looking thing of a product of two delta functions, right? And the way we deal with this product of delta functions is we take one of them and we rewrite it back in terms of the integral representation. Okay, and what we notice is that when I look at this thing, right, this is going to be my probability. This is contributing to my probability, right? The only way that this delta function is going to be non-zero is if omega equals omega fi, right? So what I can do is basically say, well, if that's the case, then I might as well just set omega equal to omega fi inside of this integral, because if it's not the case, then it doesn't matter. The whole thing is just going to be zero, right? So that's what I do, right? And then that turns this coefficient into, or turns this exponential into just 1, and then I can do the integral, right? And if I do the integral, then I just get basically t over 2, big T over 2, big T over 2 pi, sorry, right? But I'm still taking the limit as t goes to infinity, okay? But now what I can do is I can take this and feed it back into this expression up here, right? And what do I get? So I end up with this thing. So this is when I feed it back in, okay? And what am I doing here? So I'm canceling off some factors of 2 and pi, right? And I still have this limit of t as t goes to infinity, right? But what I'm after is not the probability, but after the rate, actually the average rate, right? So what I would want to do is take this probability and divide it by big T, right? That would give me the average rate. And if I do that, then that big T is going to cancel this big T, right? And the limit of 1 as T goes to infinity is just 1, right? And so what I end up with is just this prefactor again, matrix element squared, and this delta function, right? And if I express this thing in terms of energies, then I can rewrite all this stuff like this. So this is the rate, transition rate. It's an estimate for some perturbation, so some system that you put inside of some type of, or expose it to some perturbation, and you want to compute the rate, transition rates of from state I to state F. Right, and this is known as Fermi's golden rule. Okay, and I can't remember if there's a homework problem on it or not, but it's always a good thing to know. It gives you a quick way to basically compute, knowing what your states are and what your perturbation is. It gives you a quick way to compute transition rates for systems, and it's widely applicable, and it's just a good piece of physics to know. Okay, all right. So that'll do it for now, and what we'll do is pick it up next time on Monday. Keep talking about scattering theory, and we'll get into how to start computing these scattering amplitudes. Okay. All right. So everybody have a good weekend. I'll put a drop. I'll put a I'll put yeah, homework in the Dropbox, and I'll see you Monday. All right. Okay.